Hello bachcho and welcome. Today we're diving into a very important topic from moving charges and magnetism, the solenoid. It might seem a bit tricky, but I promise by the end of this session the concept will be bilkul simple and you'll be ready to confidently handle any exam question on it. So let's get started, shall we?
So let's start with a little challenge. Imagine you need a magnetic field that is perfectly strong, perfectly straight, and uniform everywhere. A single straight wire? Nah, its field goes around in circles and gets weaker as you move away, right? What about a single circular loop? Well, that's not quite uniform everywhere either. So how on earth do we solve this puzzle?
To solve this problem, we need a hero. And in the world of magnetism, the hero that gives us this perfect field is a special device called the solenoid.
So what is this solenoid? Take a look. It's surprisingly simple, isn't it? A solenoid is really just a long, insulated copper wire that's been wound very, very tightly into a coil, or what we call a helix. The NCERT textbook defines it as a long wire wound in the form of a helix, where the neighboring turns are closely spaced. That's it. That's all there is to building. Okay, so we have this simple coil of wire, but the real magic, the real action, happens when we pass an electric current through it. Let's take a look at what's going on inside.
I want you to think of it like perfect teamwork. Every single loop of the wire creates its own little magnetic field. Now, inside the coil, all these tiny fields are pointing in the very same direction. So they all add up, they cooperate, and become one super strong, unified force. But look what happens outside. The fields from the top and bottom parts of the loops point in opposite directions. So what do? They cancel each other out. It's a beautiful example of physics in action: reinforcement inside, cancellation outside.
And the result of this amazing teamwork is exactly what we were looking for. We get a powerful, uniform, straight magnetic field packed inside the solenoid and almost nothing on the outside. This uniformity, this perfect straightness, that is the solenoid superpower. Now that we know what a solenoid does, the big question is, how do we calculate the exact strength of this magnetic field? For that, we need a special tool, a master key from our physics toolbox. And that key, my friends, is Ampere's circular law. Now, don't let the name or the symbol scare you, okay? Ampere's law is simply a powerful tool. It tells us that there's a direct link between the magnetic field circulating around any closed path and the electric current that passes right through that path. We're going to use this amazing idea to unlock the formula for our solenoid.
To apply this law, we need to imagine a special rectangular path. We call this an Ampere loop. Let's label its corners A, B, C, and D, just like you see here. We'll place this imaginary rectangle so that one side, AB, is deep inside the solenoid, and the opposite side, CD, is completely outside. Now we'll check the magnetic field along all four sides of this rectangle.
Now this is the really clever part. Let's look at our path piece by piece. First, the path CD, which is outside. We already said that magnetic field B there is almost zero, right? So its contribution? Zero. Easy. Next, let's look at the side paths, BC and DA. Here, the magnetic field is horizontal, but the path is vertical. They're perpendicular, at a 90-degree angle. And in physics, the dot product of perpendicular vectors is always zero, so their contribution is also zero. So you see, 3 out of 4 sides contribute nothing. This leaves only one path that matters, the segment AB, inside the solenoid. And the current enclosed by our loop is simply the current in each wire, I, multiplied by how many turns are inside the loop, which is N times H.
So let's put it all together now. Ampere's law connects the magnetic field effect with the current inside. On one side, the only magnetic effect we have is from path AB, which gives us B times H. And on the other side, we have our constant, mu naught, times the total current we just calculated, which is N times H times I. It simplifies beautifully, doesn't it?
And now for the final step. We can see H on both sides of the equation, so we can just cancel it out. And we arrive at our final, beautiful, and very, very important formula. B equals mu naught Ni. Please, bachcho, remember this. Write it down. This is the key formula for the magnetic field inside a long solenoid. It's simply mu naught times N times I.
Theory is great, but let's make this real. Let's use our new formula to solve a typical exam problem. This one is taken straight from your NCERT textbook. It's example 4.8.
Okay, so here's our problem. We have a solenoid that is half a meter long. It has a total of 500 turns of wire, and it's carrying a current of 5 amps.
All the information we need is laid out right here in this table.
Now, the very first step, and please pay close attention here, is to find small n, the turns per unit length. We just divide the total turns, capital N, by the total length, L. So 500 divided by 0.5 gives us 1,000. Now it's easy. We just plug everything into our formula. B equals mu 0 times n times I. We substitute the values, do the quick calculation, and we get our final answer, 6.28 into 10 to the power minus 3 Tesla. See, once you know the formula and the correct value for n, it's very straightforward.
All right, now for a very important section. Let's talk about some silent killers. These are the small, common mistakes that so many students make in exams, which can cost you precious marks. So please pay close attention.
The number one exam trap, without a doubt, is confusing small n and capital N. Remember, our formula, B equals mu 0 n I, uses small n, which stands for turns per meter. But often, the exam question will give you capital N, which is the total number of turns. So your first step must always be to calculate small n by dividing the total turns n by the length L. This is such a crucial point. Don't fall into this trap.
And here are a few more key facts you must remember. First, this formula works perfectly for what we call an ideal long solenoid, one where its length is much, much greater than its radius. Second, for such an ideal solenoid, we always take the magnetic field outside to be 0. And third, the field inside is strong, it's uniform, and it's perfectly parallel to the axis of the solenoid. Keep these points in mind. Excellent! We've come a long way. Let's quickly summarize what we have learned about the solenoid and then see why this knowledge is so very useful in the real world. So why does all this matter? Well, because the solenoid's ability to create a strong, uniform magnetic field that you can switch on and off with a button makes it the absolute heart of every single electromagnet. From those giant cranes in scrapyards that can lift entire cars to the tiny relays and doorbells in our homes, the solenoid is the fundamental component that makes them work.
Okay, so for a quick revision, here are the key takeaways from our session. A solenoid is just a coil of wire that creates a strong, uniform magnetic field inside it. For an ideal solenoid, the field outside is 0. The strength of the field is given by that simple formula, B equals mu 0 Ni. And never ever forget that small n is the number of turns per unit length.
And to finish, I have a little question for you to think about. We know the magnetic field lines inside are perfectly straight and parallel, but a real solenoid isn't infinitely long. It has 2 open ends. What do you think happens to those nice, neat, parallel lines as they reach the ends and come out? How do you think they behave? Give it some thought, and we'll see you in the next class.